All right, let me wrap up this tutorial with a little discussion on what we can do and what we cannot do with this technology, and I think that will give us some perspective going forward. So before I talk about use cases for terahertz, I think it's instructive to look at how well 5G millimeter wave systems are doing and ask yourself, is this addressing a problem that we're having with 5G? So 5G systems, of course, are out today, at least in the United States. You can go and buy a 5G phone and try it out. This is what a reporter did. This is an article from this reporter's website. This was a year ago. They were still in the trial phase, and they bought a Verizon phone, and tried it out. And what that time was their trial network in Chicago. About the same time, a little bit after that, remember I was telling you about that University of Twin Cities group. They did also a very good, much more scientific study of trying out these 5G phones on this network. And if you look at both of them, you will see that you can get peak data rates in excess of 1 gigabit per second, which is really quite phenomenal relative to what you would get at 4G. But the coverage is very limited. For example, if you take this route that the researchers in this University of Minnesota Twin Cities paper did, you'll see that, okay, when you're in their 5G connectivity, you're getting 500, 600 megabits per second often, and sometimes you get peak rates that's even higher than a gigabit. It's not shown on this graph. But you have frequent fallouts because you drop coverage, and you have to go back to 4G in these cases. That comes from the fundamental coverage limitations that I mentioned in the first part, that signals get blocked by many building materials. Now, maybe this will get improved if we have networks at much higher densities, but right now, this is an issue. Now, this is all 5G, so why am I talking about this? Because all of these problems that you're going to see are going to be there in terahertz as well. You might get higher peak rates when you have coverage, but you're only going to get that coverage less frequently. And so it doesn't fundamentally address this issue. Now, an additional data point I want to put out here about 5G is where the industry is actually going. There's this academic interest in going to very high frequencies, even higher. But that's not really where a lot of the industry is concentrated. There's another great website called OpenSignal. OpenSignal has installed apps on large numbers of phones, and they measure throughput, delay, and all sorts of great statistics on commercial networks globally, and they aggregate that data. So if you go to their data set, you'll find this very interesting trend, which is, okay, so here's Verizon has a millimeter wave network, and if you limit yourself just when the 5G phones are connected to millimeter wave, and you look at the average throughputs, the average throughput is really high. It's like 500 megabits per second. Of course, peak data rates can be in excess of gigabits per second. But a large number of carriers, particularly in Europe and in Korea, have gotten very good performance with what's called the mid-band spectrum, which was the dominant, in the last number of years, has been a lot of interest by carriers in this frequency band, because you don't have quite as much bandwidth as millimeter wave, you have a large amount, and you're getting networks where you're seeing 100, 200 megabits per second. So it's less than what you have in the millimeter wave range, but it is still very high, and this has become kind of the sweet spot for a lot of operators, at least near-term plans. And this was accelerated in the United States by the recent auctions in the C-band in these frequencies. So what the trend is that as much as we might, from a research standpoint, want to look at higher frequencies, at least in the cellular space, the interest right now is at these lower mid bands, and that seems to be where that's meeting the applications that we have. Now, that is not to say that in some future cellular system, even higher frequencies of millimeter wave might be viable and might want to consider terahertz. But I think that we need to look at these limitations very seriously before we start immediately jumping to the conclusion that terahertz is going to be on every smartphone. I think the better perspective for terahertz is to think about what are new applications that go beyond your traditional smartphone use that can be enabled by these applications, that by these very high data rates that may not be possible in lower frequencies. So for the remainder of this, let me try to give you some offers of what this might be, although I'm not even these cases 100% convinced that these are applications that can't be served well with lower millimeter wave frequencies or other frequencies. So the first one I want to talk about is UAVs, which is a lot of interest, and I know some of you in this tutorial have done some excellent work in this area. So millimeter wave and terahertz, of course, are generally attractive because they have very high bandwidth and you get gains from spatial multiplexing. But they're particularly, or at least possibly, attractive for UAVs for a couple of reasons. First of all, if you're aiming up in the sky, you have a much better chance of not being blocked and getting a line of sight link, which is where these technologies really shine. You also might have more power availability because, of course, it takes sometimes into the kilowatts of power to actually drive a UAV. So then those tens of watts that might be needed on a terahertz transceiver are actually feasible, where they may not be feasible on a smartphone. And also you might have a little bit greater aperture area that you can mount depending on the size of the UAV or the ground base station, and that could enable other things like line of sight, MIMO. Now, talking about the need for high data rates, what you would do with these data rates, this table comes from this very cutely titled paper from my colleague Giovanni Garassi, what's the future of UAV will be, a flight from 5G to 6G. And so in this table, in this paper, it actually quotes another table from some 3GPP specifications on various use cases and what they might need in terms of latency and bandwidth. And let me just highlight a few of these. If you look at the ones that are using it for the purpose of surveillance, either somehow, so there's some type of either laser mapping or video, and you want to communicate that back to a ground base station, you can easily imagine getting data rates that are in the 100 megabits per second. And that might be an attractive way if we need to support large numbers of these links for terahertz. That's not to say that that is not impossible in a lower millimeter wave frequency, but if we take these systems and then either go to a much higher level of depth resolution imaging, then maybe this would actually be useful. The other part that I just want to point out here is in terms of location services. So some applications, both for UAVs, but in a variety of circumstances, may need very precise positioning. And I haven't talked much about positioning, but this is clearly an area where terahertz can benefit because it has very wide bandwidths. That means you can get that very high temporal resolution as well as angular resolution to locate objects, and that could be attractive as well. So we started looking at this problem just to get a very high, let's say, back of the envelope kind of link budget type of calculation under reasonable assumptions, comparing 140 to 28 gigahertz with the sort of power numbers that we had. And if you, this study involved we had to think fairly carefully about where we would place the arrays and did some fairly detailed modeling of the array geometry. But the upshot is this, that if you go to 140 gigahertz at a pretty reasonable bandwidth that you can get at this frequency, and just using single stream, not even line of sight MIMO, you can get up to about almost a few hundred meters. You can get about over 6 gigabits per second. and you can get over a gigabit per second, well out into 100 kilometers, and that could do significantly better than a system at 28. So if you need these very nosebleed data rates, this might be an attractive way. If we add line of sight MIMO on top of this, which I did not show, these will go up even quite significantly, because as we saw before, that when you're in that few hundreds of meters of range, you're easily in that really distance. Some researchers are even thinking about this for long distance communication. This is a really excellent paper from a group of researchers at Oulu, Tampere, and Northeastern. And what they did is kind of, again, but a very good link budget study to trying to look at whether you can have terahertz links from the ground to an aircraft, and maybe even an aircraft up to a satellite. The satellite either being a geostationary satellite, maybe about 35,000 kilometers, or a LEO satellite that maybe, say, in the order of 200 kilometers. There's a lot of interest in this. Of course, now people are talking about rural coverage, and this could be a potential solution. I didn't put it up on the slide, but I should also point out that there is movement already commercially looking at satellite systems in the 73 gigahertz band and the E band. So it's very reasonable to imagine that we could go up into that 140 gigahertz band. Now, this paper, I really strongly recommend anyone interested in takes a look at this paper. They do a very detailed link budget study. And so I just wanted to show a couple of the plots from this. The first on the plot on the top left is the path loss under different conditions for LEO and geostationary links. The x-axis is the frequency, and what you see is, of course, those big spikes are those oxygen absorption and other molecular absorption bands, which you can't transmit. But even in the other parts, that path loss is pretty daunting, things on the order of over 220 dB of path loss. But if you have the right technology, I'll return to that in a moment, right, under some assumptions, you can still get very high rates. So this was considering, let's say, a ground to aircraft and aircraft to satellite. You can get links that are, potentially in the tens or 20, up to maybe even 50 gigabits per second, at reasonable altitudes of that airplane. So this would be very, very attractive. But as the paper points out, what this needs is a very, very high gain antenna that will overcome that path loss, maybe in the order of 60, 70 dBi. If you are used to lower frequencies, that would be like the gain you would get on a deep space satellite parabolic dish, a much higher gain than what you're seeing now. Now, that paper makes the argument that this is feasible theoretically, but we're not there yet, and this could be an avenue of future research. The other aspect of this is that because of the different geometries, you might actually need multiple frequencies to get continuous different coverage. So this is a super interesting application that I think will be something that something to look at. Another pretty natural, at least near-term application is connectivity to cells. So this has been really all access technologies, even going back into the 4G time when you're looking at microcellular deployments. A continuous problem has been getting the fiber connectivity to those cells. There's other problems with just the site acquisition and so on. But at least for the fiber connectivity, when that's not possible, you might want to envision using wireless. And at this point, because this is a point-to-point link, maybe a 140 gigahertz or higher frequency terahertz link might be useful. Now, there's actually a lot of new ways that the cellular architecture is evolving to support this. As you might know, they're kind of disaggregating, if you like, the RAN, dividing the various components of the radio unit and the distributed unit and central unit, and one can use these wireless connections between any one of these. Now, we did a little bit of a capacity analysis, just ray tracing, of this work. And what, I don't want to go into details of this, but what you could get is under sort of reasonable transmit power, if you had about on the order of, say, 3 central units that were well placed, usually on tops of buildings, you could cover a reasonable area at fairly high data rates that are close to about 10 gigabits per second. That's with a single stream. You can probably get higher with line of sight MIMO. Now, so that might be also an attractive solution. Talking about line of sight MIMO, there's a very nice recent work by Ericsson in collaboration with some German academics, which have demonstrated the following system. So if you go back to the first part of the talk, I mentioned this technique that's sort of been known theoretically well called line of sight MIMO, which is that if you have a wide enough aperture array, you can transmit on multiple streams if you're within the Rayleigh distance. So this is what they did. This is their array. It's actually 4 parabolic dishes and about on a square with sides of about 1.7 meters. So they're fairly far apart to get that wide aperture, which will get higher Rayleigh distance. And then you can transmit 8 streams in principle, because you have 4 of these plus times 2 polarizations. And if you transmit at high enough data rates, you can get in this system 100 gigabits per second. But here's the amazing thing. So they deployed this. This is our section of Athens. And this is a 1.5 kilometer link. So it's very far distance away. And they could demonstrate this 100 gigabit link over that distance. And that is a very promising application of this high rate line of sight MIMO, and that maybe could be applied in other scenarios as well. Final topic that I will just quickly mention, and I didn't get enough chance in this to talk about imaging, is the use of radar. So we're already seeing this is probably the most immediate short-term benefit of terahertz, because it has very obvious benefits. Obviously, radar will benefit whenever you can have a very narrow angular resolution, and will also have very benefit from the very high temporal resolution. What you saw commercially is that in the automotive space, the radar systems had already gone from 24 gigahertz to 77 gigahertz to benefit from the higher frequencies. So it's very natural to go up to higher frequencies. This paper here gives kind of a very nice summary of some FMCW radars, both in SIGI and CMOS. And you can see some pretty interesting numbers. So first of all, these carrier frequencies that people are thinking of range from 200 to maybe even to 375 gigahertz with very, very wide bandwidths, which are just not at all available at lower frequencies, things like even up to 70 gigahertz of bandwidth or 100 gigahertz of bandwidth, and with reasonable output powers. And this could improve the output power if some of those newer devices that I had mentioned in the previous section come along. Of course, the noise figure is a bit of a problem, but I think we'll have better technologies to deal with these. But overall, these power consumptions are definitely reasonable in a lot of, say, automotive applications or other things like this. So this, I think, will be a very attractive area if you are a radar signal processing person. I think this is an area that could be very interesting to jump into. All right. That's all I want to say about use cases. So let me just wrap this up and wrap up this tutorial. Let me just be kind of realistic, is that terahertz is not for everything. It has very significant limitations. It suffers from the high power consumption and relatively poor coverage. And I think right now, at least, and maybe it'll be interesting in the discussion section, someone can argue with me that at least thinking about it as a conventional modem in a smartphone is maybe not the right or best use case for it. And we really need to think about what are new use cases that can motivate this technology. I've suggested some of them, almost I think the best cases for that really is imaging and radar, but also backhaul point-to-point links and maybe aerial links as just some examples. And I'm sure we'll see some new applications, probably by some of you also who are in this audience right now. So that wraps up this tutorial. I hope you enjoyed it. This was a very thin little slice of terahertz, and there's a lot of great research that I did not have a chance to mention. If you have any questions, feel free to shoot me an email. I'll love to talk about the topic, and I just again want to thank all the sponsors for their research, including the affiliates at NYU Wireless, the National Science Foundation, and the Semiconductor Research Corporation. And of course, thank you to SPAWC and all the organizers for giving me a chance to speak here today.